So now I'm going to talk about uniform and Gaussian distributions. Before we start, let's just think about what the area under a probability distribution would be. So what would the overall area under a probability distribution be? And you should know that basically if we integrate any probability distribution, the answer is always going to be 1, because overall, out of all the things that can happen, they've all got to happen with probability 1. Now we're going to think about a uniform distribution, and we're going to think of that in terms of a random variable x, which is restricted to a value which is finite over a range from A to B, and it will have a constant density at that point. So let's just write that down a little bit more clearly. The function of this variable x is going to be equal to some constant value over the range A to B, and it'll be 0 outside. Now, the reason that we have a factor of 1 divided by b minus a as being the density value is because, like we just said, the area under the curve has got to be 1 overall. So if we actually look at what this looks like when we plot it out, this density function, which is uniform between a and b, has a 0 density outside that region and a density within that region corresponding to b minus a. And the reason for that is because basically we want to make sure that when we integrate this thing, we end up with a value of unity. And if that will be the case, the distance here is b minus a. The height here is 1 divided by b minus a. So if you multiply, in this particular case, the height by the width, we get a value of 1. That's just doing it from first principles, which is really easy because it's nice and rectangular. And something which, for example, would come from that kind of distribution would be like the angle theta of a second hand on a watch that goes round. It's uniformly somewhere between 0 and 360 degrees on the watch face. So as we said, the total probability of an event, which we get by integrating the distribution, has got to be 1. So the area under it has got to be 1. We can also look at that in a little bit more formally and say, let's just try doing that. If we wanted to work out what the area under this curve is, and it was a general curve of functional form fx, so we'd say basically we have to integrate between b and a fx dx. And we'd end up, obviously the dx goes to 1, and then we basically have to substitute in this factor here, 1 divided by b minus a for the fx, and then we evaluate between b and a. So basically we end up with b minus a divided by b minus a, which ends up with a value of 1. So that's what we started with. That was very easy. The only advantage of trying to do it a little bit more rigorously like this is because if the function isn't something simple like 1 divided by b minus a, then obviously you need to integrate something, and although we can do this by inspection, if it was a more complicated function you'd need to do the integral. So, simple question then, if we've got this uniform distribution and now it goes between 0 and 1, what is the probability that x will be between 0 and 0.5? Now you should actually know how to do that from what we discussed earlier. What I'm really saying is, what is the probability, and this is plotting it out, that we're going to get a value sample from this distribution which is between 0 and 0.5, and it will of course correspond to this blue area, and we can see just by inspection again, right, we can just see that that's going to correspond to a value of 0.5 just by saying it's half of the size of the area that we have in all. But we could just do it again by integration. So what we do is we integrate 1 dx, because we've got 1, the value of px is 1, 1 dx between 0 and 0.5. 1 goes to the x, and then we have to evaluate it between the limits of 0.5 and 1, and we see that we end up with 0.5. So that's doing it a bit more rigorously rather than just looking at it. So what's the expected value of a function? Well, if we got something discrete, then it's the sum for all of the events of the value times the probability of the value. So we basically just multiply the value of something by the probability that it occurs, and just adds them up, and then add them up for all possible events. So here xi is a data sample, pxi is the probability that that actually occurs. More simply, basically, it comes down to the following formula. If all the events are equally likely, right? If they're equally likely, when we end up with, and the probability of each event can be approximated by 1 divided by n. Therefore, what we do is we'd evaluate this formula. The p of x is now a 1 divided by n, so we end up with a sum across all of the elements divided by n, and this gives us the expected value, which is the mean. Right, so xi data value, n is the total number of data points or data samples in this case. Now, if we want to actually deal with a continuous set of functions, then rather than doing the integral, right, so rather than integrating over all individual samples or all individual events, what we do is rather than summing them up, we actually integrate across them instead. So rather than having a sum, we now have an integral. So it's going to be xi multiplied by the probability that that particular value occurs, dx, and then just integrate across all the range of x. Okay, so xi is a data value at sample or value I in this case, and probability is given by the pxi term. So let's think about how we could calculate the expected value of a uniform distribution between 0 and 1. So obviously the density is going to be px equals 1. It looks like that, like it did before. What is going to be the expected value? Well, we've already worked it out, haven't we? We can kind of say it's easy to do it. So what it's saying is, first of all, what's the area under this distribution? Well, we already know that that's 1, but the expected value is given by the formula that we just looked at. So we have to integrate across x is going to go from 0 to 1. Xi multiplied by the probability of each value at that point. And we see the probability of each value at that point is going to be 1, right? So we can substitute in, first of all, the limits between 0 and 1, x times 1, so p the probability is going to be, density is going to be 1, dx, and we just have to integrate x dx basically, and we end up with x squared over 2, and then we have to evaluate between 1 and 0. So we basically substitute the 1 in, the 0 obviously has a 0 effect, and we end up with half. So as you'd expect then, looking at this uniform distribution that we've got here, the expected value of this uniform distribution, which is uniform between 0 and 1, is 0.5, which is kind of where you'd expect it to be. It's basically the middle value, right? We can also define what the variance is for a variable as well, and the variable sigma basically relates to standard deviation, which is, and sigma squared is the variance, and we can calculate that in this case for a set of discrete events by doing the following. We get the data sample or the event, and we take away the overall mean, we square that, and then multiply by the probability that this event has happened, and we sum up across all events. Okay, so xi is the value of the data sample, mu is the sample mean, p x of I is the probability that this thing actually occurs. Again, like I said, sigma squared is the way we write down variance quite a lot. In the case where each one of these events is equally likely, we'd have the probability again, since we're summing up over n, we'd have it as 1 over n. In actual fact, what you actually see when you're calculating standard deviation and variance is generally we want what's called an unbiased estimate, and basically that results in the fact that rather than dividing by n, we divide by n minus 1. That's a little bit outside the scope of this particular lecture series, but I'm sure the statistical lectures have explained what bias is to you already. In the continuous case then, rather than having a sum across, or basically a sum across all weighted squared differences from the mean multiplied by the probability. What we do is we use an integral again. So we integrate in this case. In fact, we're integrating from minus to plus infinity. Again, we calculate the value of x, take away the mean, we square it, and we multiply by the probability of that particular value occurring. So it would be the density in the case of a continuous variable. We can also calculate something called the covariance, and this is basically something that you need to calculate when you've got more than one dimension in your function or in your data set. And obviously variance is just basically x take away its mean squared, and then you calculate the expectation of that. Covariance is slightly different. It's if this is two-dimensional and we've got x as one dimension and y as the second, it will be x take away its mean multiplied by y take away its mean, and then we calculate the expected value of that. And again, to calculate the expected value, all we have to do is basically add them up and divide by the total number if we're doing it with discrete cases, or we have to do an integral if we're doing a continuous case. So basically expanding our expectation function to give the covariance xy, this is what it looks like. Basically what we have to do then is we have to sum up all of these terms across all the events we have. So if there's, in the case of data samples, we'd have I is a sample number. In this case we've got capital N samples. Then for each value, for each sample, you basically, first of all, you'd calculate the mean in the x dimension, the mean in the y dimension, and then you'd calculate for each sample the sample x value take away its mean multiplied by the y sample value take away its mean, multiplied them by the probability that those things occur. So just like I said before, that's just for your information. So this can also be written in this form when we have basically the assumption that all samples are equally likely. So if they're all equally likely, this probability term is going to be, if there's n of them, it's going to be 1 over n. Again, rather than having a 1 over n term, we have an n minus 1 because we will need to, again, we need to deal with bias. And we end up then writing it in this form. This goes to the sum across all data points or all events. X take away its mean, and x hat is sometimes used to represent its mean, and multiplied by y take away y hat, again divided by n minus 1, so it's an unbiased estimate. Now quite often we can use the Gaussian distribution to characterize data sets, because it does fit quite well to quite a lot of data sources. And if it doesn't fit on its own, then we can sometimes use mixes of Gaussians, and we'll come to that later in the course. The functional form of the Gaussian in one dimension is as follows. We've got this exponential term here. Let's look at that first. E to the minus x minus mu squared divided by 2 sigma squared. So first of all, it's basically, this is looking at how far it is away from the mean, but it's squaring it, right? So you lose, because of that, you lose the sign. That makes it symmetrical about that point, basically, whether or not it's positive or negative away from the mean. And then this scaling factor on this exponential is given by 2 times the variance. And it's an exponential decay around that point. So this particular part of the expression, the e to the minus x minus mu squared divided by 2 sigma squared, leads to the fact that you get a rapidly falling off exponential this way, which is a sort of squared exponential, but it's also symmetric because there's a squaring effect. The thing at the front here, this term at the front, 1 divided by sigma, the square root of 2 pi, is really a scaling factor, right? So if we integrated this expression, this is f of x, this is the density for this Gaussian distribution, of course we end up with a value of 1, right? Because you've got to have an area of 1 underneath a a probability distribution. So this factor in front of that, if you like, is it needs to be there in order to make sure that it does actually end up having an integrated value of 1. So you have a value of 1 underneath the curve. Now, just looking at this curve in blue, this is when we've got a mean of 0. We haven't actually written it on the thing, but that would be a 0 point there, right? And we've got a certain value of variance of 0.2. Now, what you notice is that in this particular case, it's quite a sharp curve. But when I've got a sigma squared of 1, that's 1 standard deviation. We see it's already getting a bit broader. And then we go to 5, this is the yellow one, we've got a lot broader. So the variance basically spreads out the distribution, right? The bigger the variance, the more spread the values are. And this is exactly what we saw when we were plotting those two-dimensional clouds of points, right? When the variance gets bigger, we get a bigger spread. And all we actually do by shifting the mean, if we change the mean to -2, for example, if we compare, we can't quite compare it with anything else we've got on there, but basically, as we change the mean value, all we do is shift it along the x-axis. So this has got a mean, all of these have got a mean of 0, and this has got a mean of -2. It doesn't actually say on here, unfortunately. Right. Now, this also basically introduces the idea of what's called sufficient statistics. And basically, for a distribution, the sufficient statistics are the things you need to know in order to specify that particular distribution. And in the case of a Gaussian distribution, in this particular case of one-dimensional, all we need to know is the mean and the standard deviation, or obviously that's equivalent to having to know the variance, right? And that's just to make sure that you know what the terms mean. So what's the relevance of standard deviation? Well, like I said, it gives you an indication of the spread of the distribution when it's a Gaussian distribution, and so you have a sort of a kind of a feeling of what kind of a spread you get with a standard deviation of 1. Basically, it would mean that we have 68% of all the data points. Well, the probability is 0.68 that that if we sample this, probability is 0.68 that we'd get a value within 1 standard deviation from the mean, right? So if we had a much bigger, well, twice the size of standard deviation, so we have and now we've got a Gaussian with a standard deviation of 2, then the probability that we get a sample from this within 2 standard deviations is 0.95. So you can see, you know, basically when you start making the standard deviations wider, this starts rapidly accounting for all of the data that you're going to get by sampling a distribution. Okay. So we can also calculate a cumulative distribution. Basically, this is just the area under the probability curve to the left of the point that we're interested in. We did talk about that before. So all it's saying is the cumulative density basically is just the area under the Gaussian, in this case it's a Gaussian, to the left. So it's all of this stuff here. So as I start off with x equals -3, there's virtually nothing underneath the curve. So if we look along here on the cumulative distribution function, we see we've got an almost 0 value here. And as I move along here with the x, and in fact I'm moving all the way to here, what we see is we get more and more and more of the area. In the middle region, it starts rapidly adding up, and as we get, well, to start with, it builds up slowly, and at the end it dies off slowly. So that's why we get this kind of sigmoid kind of response here, which starts off at 0. When it gets to the mean, it's halfway through, right? So it's got a value of 0.5, and then when we get to the end, it goes to 1. And as I said, at the edges, this lower limit and the upper limit, you get this squashing effect towards the asymptotic values of 0 and 1. Now, obviously, we're going to be doing a lot of work with things which are much more dimensional than just a single measurement. So we have to look at multidimensional distributions as well. And there is a formula which lets you, well, this is basically the formula for a multidimensional Gaussian, right? So let's just think about what the terms are here. Let's start off with the exponential term, and you can see it's kind of similar to what we had for the one-dimensional case, except now it's all written in vector form. We've got a minus 1 over 2 scaling factor in front of it all. Then we've got the vector x, take away the mean vector mu, transposed, multiplied by the inverse of the covariance matrix, then multiplied by the vector x minus mu again, right? So before this was just x, this was just mu, this was just basically 1 divided by sigma squared, but now as you can see it's the inverse of the covariance matrix, and these previously were single values, but now they're actually vectors. And in front here we've got again another scaling factor just to make sure the overall area under this multi-dimensional probability distribution, to make sure that it actually adds up or sums to 1 when we integrate it. And there's got this factor 1 divided by the square root of 2 pi to the power k, well that's the dimensionality, multiplied by the determinant of the covariance matrix. And we'll talk a little bit about the covariance and the mean in a sec. So let's think about covariance again. We did mention this quite a little bit before. Covariance is then how two features vary, right? How do they vary? If covariance of let's say feature A and feature B are positively correlated, well, if the covariance is positive, then it means they're positively correlated. If they're negative, it means they're inversely correlated. And if they're 0, it means they're completely independent. And we saw that when we were plotting out clouds of points, right? So if we plot things out from something where the two features are completely independent, we get this nice spherical cloud, provided we plot it in the same range on both axes. And if x and y are very correlated, we tend to get things along a diagonal. So in the case of then, just going through it one more time, the covariance matrix for a 2 by 2, for a two-dimensional data set, we have a 2 by 2 covariance matrix. We have 4 terms in this, of course. The top one term, basically here, is the variance of feature 1. Let's go right down to the bottom one here. This is the 2 term. This is the variance of feature 2. And then these 2 areas here, this is element 1, 2. This is then the covariance of x1 and x2, and then this element here, 2, 1, is going to be the covariance of x2 and x1, right? And these variances represent the variances of the features, and the covariances then give us an indication of whether or not the things are actually correlated or actually independent. So let's now just look at a little bit at the multi-dimensional Gaussian distribution. And basically it's given by this expression that we've just seen. It's sometimes also written in machine learning literature or communications literature in a shorthand notation. So rather than writing all of this out, quite often people say it's a normal distribution, n, with parameters mu hat and sigma, so in other words with a mean vector and sigma for a covariance matrix. And this, this captures an awful lot, a lot of detail when you think about it. So let's expand this out so we can look at it in terms of what we can understand in terms of one-dimensional vectors, one-dimensional quantities sometimes. If we then expand this thing out, what that means is we need to go through each term and evaluate it. So let's just go through and explain where everything comes from. So let's start at the front. We've got 2 pi. 2 pi is easy. That's just a scaling factor multiplied by sigma, and then we take the determinant of all that, and then basically raise it to the power 0.5, or divided by the power minus a half. So sigma we can expand out in terms of its 4 elements, because we're just saying it's now going to be a 2-dimensional data set. So this is sigma 1, 1, sigma 1, 2, sigma 2, 1, sigma 2, 2. So the 1, 1 is the variance of feature 1, the 2, 2 is the variance of feature 2, the the sigma 1, 2 is the covariance of 1 and 2, and sigma 2, 1 is the covariance of 2 and 1. Then what we do is we're going to start expanding out this expression here. So exp stays the same, minus half stays the same. Now we're going to expand out y hat as being a two-dimensional vector, right? So y1 and y2 are the elements. Mu is now going to be expanded out in terms of mu1 and mu2. This whole expression is transposed. It's multiplied by the inverse of our covariance matrix, and again we've expanded out all of those terms, and then we multiply it again by y, take away, in this case, mu, right? So we've got the y1, y2, take away mu1, mu2. So it's easy to work out what the determinant is for this 2 by 2 matrix. It's this term times this term, so that times that, take away that times that, right? So we can write those in a simplified way. We can also easily calculate the inverse of the covariance matrix. First of all, it's 1 divided by the determinant, and then all we have to do is flip these two over here, right? These flip over, and we change the sign of these two. So that these flip over in location, and then we change the size of these two. So we can plug all of that in, and you see where it's coming from. You basically just have to put those expressions in where we had here we had the determinant term, and here we had the inverse matrix term. So we've now calculated those. So now let's think about making some assumptions. Imagine now that the system is actually using data which is uncorrelated, so there is actually no covariance. In that particular case, for an uncorrelated system, what you're going to see is the covariance terms go to 0. So these terms go to 0, right? These two here. So let's multiply that out now and see what we get, right? And what you're going to get, if you go through it all, it's going to be, obviously it's rows by columns basically, but try it yourselves. The easiest way to multiply this out is to maybe do this bit first, right? So it's this times this plus this times this. So this term just goes to y1 minus mu1 divided by sigma 1, 1. And then we're going to end up multiplying that again by this is a transpose thing this time, so we end up actually multiplying by the same thing again. So we end up squaring this term. And when you multiply the other bit out, you'll see you're going to add on the second term here, which is going to come out as y squared minus mu squared, mu2 squared divided by sigma 2, 2. So what happens then when we've got independent features is this simplifies the situation quite a lot, and we can now write this in terms of the exponential of a sum of two parts, right? But because it's a sum of two parts, we know, because we're writing things in terms of exponentials, we can expand that out in terms of the product of these individual parts. So what we end up with then, we've got this expression here, which we can just write as 1 divided by the square root of 2 pi sigma 1, 1. What we get here then is just exponential of this bit here, right? That goes to this bit here. Then we take out the scaling factor again and put it in front of here. So if you see they've multiplied this scaling factor with this scaling factor, you end up with this scaling factor. And this time we have this expression y2 minus mu2 squared divided by sigma 2, 2. And what this is showing you then, quite simply, is that when we have independent features, basically the overall two-dimensional, in this case, distribution can be built up by just multiplying the two one-dimensional distributions together. In fact, we'll come to that again later in the lecture course, because that is going to be used for the naive Bayes approximation.